Again, it's a redskin.
What is going on, guys? Welcome back. In today's video I'm going to show you how you can hide secret messages or even whole executable files inside of PNG images using Python. And we're going to do that using two approaches. The first one is a very simple, easy to understand, but also easy to detect approach. And the second one is more technical, more complex, but also more professional and harder to detect. Now, I have a very similar video on JPEG files already, but there we only covered the simple approach of appending at the end of the file. Today we're going to do the same thing for PNG files, but we're also going to cover the more complicated LSB approach, so least significant bit encoding, where we're going to use the least significant bits of the individual pixels to encode messages there. So the first approach doesn't change the image at all, and the second one changes it in a very tiny way so we don't actually notice, which means that we have a PNG file that looks exactly like the original, but we have some secret message in it that we can read, that we can extract using Python. And we can also hide executables and extract the same executables out of the image again. So I think this is quite interesting. Let us get right into it. What we need to cover first, though, is some theoretical background on PNG files. And for that, I have prepared these notes here. What you need to know about PNG files is that they always start with the same signature and they always end with the same chunk. So the first 8 bytes will always look like that, and the last 12 bytes will always look like that. This is the IEND chunk. So when you find IEND in a PNG file, this basically means that from this point on, so after this IEND, after this thing here in the end, nothing is processed by image viewers or image editing programs because it doesn't belong to the PNG file anymore. So whatever you append after that is going to be basically ignored, but you can still extract it. So the basic structures, we have these 8 bytes representing the file signature. Then we have the header. Then we have a palette, maybe if we have one, some image data, which is basically the pixels, and then we have the end of the file. And whatever we put after this here is going to be our secret message that we can enter there and we can also extract. So in order to see that this is actually the case, we can open up the Windows terminal or the Windows subsystem for Linux to perform a hex dump on a PNG file. So we can go to neural dir in my case and to the steganography, and then I can just call hex dump -c on flower.png. You don't need to do that for the tutorial. This is just to see that what I just told you is actually true. So this gives you the hex version of all the bytes of the image file. And you can see here in the end, I and B, these 8 bytes are always there. Now, I don't think that the buffer is large enough to show you the beginning of the file. No, but essentially it starts like that and it ends like that. And the ending is the more important part anyways. So how can we use that now? We have this flower.png. We want to hide something in there. How we can do that is we can define the end sequence of a hex file. So end hex is, and then B for bytes. And then we just take the bytes that we just talked about from the notes, because this is how the file ends. We can copy that, we can paste that, and essentially in order to actually turn this into a byte, we just need to say \x, because that is how you format bytes. So \x00, \x49, \x45, for E, 44, AE, 42, 60, and then 82. So this is the end of the PNG image data, or of the PNG image file. We can still have something after that, but everything that's after that is suspicious because it doesn't belong to the PNG file. It's a payload, so to say. So what we can do now is we can just say open, and maybe we should make a copy because we don't want to waste the file. So I'm going to copy it and work on a copy of this file. So paste, and we're going to call this image.png. So we're going to work with this file, image.png. We're going to open this in reading bytes mode. We're actually writing bytes mode. We're actually appending bytes mode because we don't want to overwrite it. So we're going to open this as F, and all we want to do is want to write hello world, this is my secret. And of course, we want to turn this into a byte string, byte stream. There you go. And this essentially puts this message into the image file. And I can also now go ahead, or actually let's just run this. If I now go ahead and run this script, we're going to see that the image itself still looks the same. So it doesn't look different. We can also see the original here. If I change the images here, you can see there's no difference, but one of them now contains a secret message. I can delete this now and I can extract this secret message by saying with open image.png in reading bytes mode, SF, and then I say the content of the file is f.read. And what I want to do is I want to calculate the offset. The offset is essentially the content, the index at which I can find the end hex sequence. And then essentially I say fseek offset plus the length of the end hex. So we want to go after that. We want to find the position where it starts. And then we want to go, in this case, 12 bytes after that. And then we want to say print whatever is there after this ending sequence. So I can run this and you can see here, hello world, this is my secret. I loaded this from the image itself. Now, the same thing can be used to put an executable like the Process Explorer here. I can show you that this is an actual Process Explorer. Just open it in the Explorer. And then you should be able to see that this is an actual executable file that works. So it's going to take some time since I'm recording. This is the Process Explorer. This is an executable file. I can now put this into the image. So I can say with open index. Maybe I should make another copy because now we already have some data in there. So let me just copy this again to have a fresh file that doesn't have anything in it. Image.png. There you go. So image.png. In writing bytes mode or appending bytes mode, SF. And we also want to open the Process Explorer 64 executable in reading bytes mode, SE in this case. Now, am I blocking this? No, I'm not. Yeah, so we open both streams, and what we do then is we say f.write, so append to the image whatever we read from E. That's it. We read the bytes from the executable and we append them to the image. That's all we need to do now. So I can run this. And you're going to see that if I open the image, it's still the same image. You cannot see any difference. Again, there you go, the comparison. And now if I go ahead and say, okay, delete that. I want to now extract the executable from that file. All I need to do is I need to say with open image.png reading bytes mode SF. And then again, content equals whatever is in that file. Then the offset is going to be the index of the end sequence. And then we're going to say that we move to the point where the offset is, plus the length of the hex sequence, so 12 bytes. And once we're there, we're going to create a new file, new exe.exe, write bytes, SE. And then we're going to say e.write whatever I get from that. So remember, we appended the executable bytes. The bytes of the Process Explorer are appended after this sequence. So what we do is we navigate to the end of this sequence, and then everything that comes after that are the bytes of the executable. So we basically read them and write them into a new file, new exe.exe. So I can run this now. And you see I have this new executable here. I can open it in the Explorer again. And what you see right away is that it has the same icon, has the same size. So if I double click the new executable that I just took out of an image, out of a PNG image, that I can run this, and I have the Process Explorer here again. Now this was already quite interesting and quite impressive, but the problem is that this technique is easily detectable. All we need to do is we need to jump to the IN tag, and if we find any bytes after that, we know that there's a secret message, we know that there's a payload, and we can just extract it. A more professional way is to use LSB, so least significant bit encoding. which basically means that we take the individual pixels, so we change the image slightly, and we basically just manipulate the least significant bit, so the last bit of the value for the respective channel and pixel. And by using these bits, by chaining up these bits, we have then bytes. So 1 byte is 8-bit, and 1 byte represents an ASCII character, and these ASCII characters represent then a message if you chain them together. And that's basically what we're going to do here. Now, this is going to be more complex and more technical, but we're going to learn a lot here. It's going to be quite interesting, so I recommend you stick until the end of the video. And what we're going to need is we're going to need NumPy as NP, and we're going to need pil.image. Now, if you don't have these two libraries installed, you're going to need to open up CMD and say pip install NumPy and pip install pillow. Those are the two things that you need. Once you have those, what we're going to do is we're going to define a message that we want to hide. So message to hide. In my case, this is going to be, this is my secret message, like that. Then we can load the image. I have created a fresh copy here, so this is without any payload. Image equals pil.image.open, and we open the image.png in reading mode. And then we get the width and the height by saying image.size. And then we turn this into an array. So image array equals np array list image.get data. Like that. So now we have this NumPy array and we can manipulate everything manually. The important thing is that we need to know how many channels we have. And we can do that by looking at the mode. So we can say channels, and we're going to use a ternary operation here. We're going to have 4 channels if the image mode is RGBA. RGBA stands for red, green, blue, alpha, which means transparency. If it's RGB, we have 3 channels. If it's RGBA, we have 4 channels. So else 3. And there's also the special case that we use a palette. And in this case, we're going to have the image mode being equal to P. So what we're going to do is if image mode is equal to P, then we cannot work with that because this mode supports 256 colors and works in a different way. So we're going to just say not supported, exit. We only can do that with RGBA or with RGB PNG files. So now we have the number of channels. We can calculate the pixels that we have. So basically just image array dot size divided by channels. And then we also define a stop indicator. This stop indicator, you have to think of it like that. We have a lot of pixels and we're not going to necessarily need all of them. So I don't know, let's say we have 1,000 pixels, just an example, and my message has, I don't know, to encode my message, I need 50 pixels, or let's say 300 pixels. The thing is, I need to know when to stop, and I also need to know when there is a message. So I need to have a keyword that I can read, and I can say, okay, there is something in there. I saw this tag that I defined, so there is a secret message. Of course, the two people communicating need to know that if you're sending this to someone. But essentially, you know, there you can stop, and you also know this is the proof that there is something in there. So we're going to pick as a stop indicator just a basic $neural $. Just made this up now. So this stop indicator has also a length. We're going to just call this length stop indicator. And then we're going to not only encode the message to hide, we're going to also encode the stop indicator. So message to hide plus equals stop indicator. So we're going to write it right after the message. And that's basically it. Now, what we need to do in order to be able to encode this message now, because this message right now is a string, we need to encode it into not only bytes, but bits actually. We want to have individual zeros and ones. So we don't want to just take individual characters and represent them as bytes because bytes are too large. We can only flip a bit. So we can only store a bit, 0 or 1. So in order to do that, what we do is we say byte message equals, and then we join on an empty string here, we join. This is now a little bit more complicated. We call the ort function, which gives us the ASCII representation of a character. We call the ort function on C. We're going to define C in a second. And we format it with the following format, 08B. This is just something that you have to know. 08B represents something as zeros and ones. And then we basically say for C in message to hide. So for each character, we represent this character as a sequence of zeros and ones. We can print that actually, so you can see what exactly this is doing. And the message we came up with looks like that, represented as zeros and ones. So think about it like that. You have a character, for example, A, and I don't know what exactly is now the code for A. Was it something like 40, 42? I don't know. Let's say 42 is right, even if it probably isn't. So we have this A, and it has some ASCII representation, and this ASCII representation has then a representation with zeros and ones. So the number 42 can be represented in binary, and this is what we get here. All these characters chained up as zeros and ones, and this is what we're going to use to put these bits into the actual image. So the byte message and the amount of bits we have here is essentially the length of the byte message. This is important, of course, because if the image is not large enough and we don't have enough pixels to store all these bits, then we cannot encode the message, because we need to have enough space. We need to have enough pixels that we can choose the least significant bit for. So this brings us to, if the bits are larger than the pixels that we have, then we have to say not enough space to encode the data. So this is a problem. Otherwise, however, we can start with the encoding, and the encoding is actually not too difficult. We start with an index 0. So this is basically just which bit are we encoding now. We start with the first bit, so the 0 index bit. And we say for I in range, and for each pixel that we have at least 3 channels. So in range 03, so 012, RGB. And for each channel, we're going to take the value of this particular pixel in this particular channel, and we're going to flip the last bit. So we're going to say if the index is less than bit, so if we still want to encode something, if we're not done yet, we're going to say the image array at the position ij, so pixel I, channel j. Here we're going to call int bin for binary, image array I, j. And what we want to do here, the representation is the following. It looks like that. We have 0b, I think, and then we have the number. So we want to cut off the first 2 because those are just indicating that this is binary. And then if we have that, we want to replace this last bit here. We want to change it into another bit. So we take that and we say from 2, omitting the first 2, and then up until 1 before end. So we remove the first 2 and we remove the last one, and then we basically say byte message index. So we take from the byte message that we have, or from the bit message actually that we have, the respective index that we're at right now, and we put this into the image array, so into this position here. And then we just say index plus equals 1. That's basically the whole process. Now we only need to save that, so we have the image array, which we need to reshape now into the right format. So height, width, channels. And the result is then a pill.image from array. So we turn this again into a image. Pill image from array. Image array.s type uint8 image mode, and then result.save. Let's call this encoded.png. Now let's see if we didn't make any mistakes. This should hopefully work. So now it's done at least, and we can see that we have this file here. Now you can already compare it. If you look very closely, if you look at it mathematically, you're going to see that the pixels are not the same, at least some of them. but just by looking at the images, you cannot really see a difference. So I cannot see a difference. It's the same image to me. It is actually not, but it is the same. It looks like the same image to me. And this image now has this message and also the stop indicator encoded in its pixels, not at the end of the file so that it can be easily detected. No, inside of the pixels, in the last bits, we have our message. This is very interesting. And now we're going to build a script to take it out from there, so to extract the information. All right, so let us now extract the information from the image. We're going to create a new Python script. We're going to call it extract.py. And here again, we're going to import numpy snp. We're going to import pill.image. And then we're going to say the image, we're going to open it up again. So pill image open, this time the encoded.png. In reading mode, we're going to say again, image array equals np array list image dot get data. We're going to again see how many channels it has. So if image mode equals RGBA, then 4, otherwise 3. And then we also say again, pixels equals, what was it? Image array size divided by channels, like that. And then all we need to do is we need to extract the least significant bits of all pixels. So we say secret bits, and we're going to use a list comprehension for that. We're going to say bin for the binary representation of the image array at a certain position, ij. This is a list comprehension, so we're going to define ij in a second. We're going to take from that, ignore the first two, take the last bit. I don't even know if we need that, but I'm not going to mess around with my prepared code now because otherwise maybe something happens and I don't know how to fix it. So now actually we don't need that. We don't need that. We just need the last bit. So we take the least significant bit of the respective pixel in the respective channel. For I in range pixels, for j in range 0,3. So this gives us a list of all the least significant bits for each pixel and each channel. And then what we do is we say secret bits equals an empty string join the secret bits so that we have a string actually. And then we say secret bits. And what we're going to do now is we're going to group them into bytes, because again, 1 byte is 8-bit. We now have all these bits chained together, so we want to have groups of 8 so that we have individual bytes, because we cannot translate bits into ASCII characters. We can only translate bytes, so we need to group them in groups of 8. Essentially what we do is we say secret bits I up until I plus 8, so always a range of 8. And then we basically say for I in range 0 up until length of the secret bits with a step size of 8. So we can print that to see what this looks like. This would give us pairs of, or not pairs, but collections of always 8 bits. So we would have a list of bytes now. It takes quite some time, but there you go. This is what we have now. We have these bytes represented as binary, so as bits basically, as chains of 8 bits. Now we can construct a secret message out of that. So secret message equals, and then we have the character, which is the opposite of the ORT. So we don't take now the number of a character, but the character of a number. And the number is the secret bits I. Don't autocomplete, please. The secret bits I. And then we say for I in range length secret bits. Is that correct? So here again we have all these 8-bit lists, and we basically take them and turn them into an integer. We take then whatever that means in ASCII, and now we have a collection a list of the individual characters that these bits represent, or these bytes represent. So we can now go ahead and join this again to a string. So secret message equals join the secret message, the individual characters to one string. And all we need to do now in order to find the message, or to see if there's any message at all, we need to define the stop indicator to be the same as before. So $null $, and then if the stop indicator is present in the final secret message, then we can print the secret message up until the point where the stop indicator occurs in the secret message, because after that we don't really care about whatever is part of the message. And otherwise, if there is no $null $, we have to say that we couldn't find secret message. There you go. So let's run this, and this will take some time. There you go. This is my secret message. It extracted it from the bits, from the least significant bits of the individual pixels. And again, to prove it to you, these two images look basically the same. There's no difference for us. If we look at this, of course, the pixels are different, but we cannot see it because they're so insignificant. The bits that we change are so insignificant that we don't really notice that. So let's one more time recap what we're doing. We're choosing a message, we're opening the image, turning it into a NumPy array, calculating how many channels we have there, RGB or RGBA. We define a stop indicator, and then for each pixel, we have 3 channels, RGB. These have values, how much blue, how much green, how much red. And these values are numbers represented as by zeros and ones, fundamentally. And we take the last bit, so the most, the least significant bit, or the most insignificant bit of the number, we change it. And then we do that a couple of pixels in a row. And these bits then represent our ASCII characters of the message. We put them into the individual pixels, and since we know the structure, we can do the same thing to get them. So for each pixel, we extract the least significant bit, we group them into 8-bit collections, so into bytes. We take these bytes, convert them into characters, and then we can see the secret message. This is my secret message. And I think that is really impressive. So that's it for today's video. Hope you enjoyed and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.